Okay, so this is the outline for chapter 26 about the current and resistance or resistor. Okay, so first we will introduce what is a current. Actually, we already used that before, so it's a bit strange to really introduce this electric current here. But anyway, we will introduce it, and then we will also talk about what is a current density. Current density is like it's actually related to the current. Okay, which is like the surface integral of the current density will be the electric current. But the current is a scalar. Current is a scalar, and the current density will be like a vector field. So so it will be a bit more complicated. Then we'll talk about resistance and resistivity, which is the characteristic of some of the conductor, or actually even for non-conductor, we can define the resistance. And then we'll talk about the Ohm's law, but of course this is easy, so I suppose you should have known it. And then we'll talk about power, and slightly talk about semiconductor and superconductor. Okay, so here we talk about the electric current. So any isolated conducting loop, regardless of whether it has excess charge, is all at the same potential. Okay, so this is very trivial. So as much as this is a conductor, we will consider the potential over the whole conductor will be the same. Okay, no electric field can exist within it or along its surface. So this is what I've mentioned for several times. The E field inside the conductor should be zero, or even at the surface. So at the surface is like a boundary. So yeah, you cannot even define the E field, because if you really consider the equation like dE equals k times dq over r squared. If r is zero, then it is infinity. So actually dE is not defined on the surface, I would say. But anyway, we don't consider this kind of strange problem. Okay, so so here we try to do something strange, and then which means that we try to make things complicated. We try to put a battery for the loop. Then for this one is a battery, so it will provide a potential difference. So this one is a positive node, this one is a negative terminal. So yeah, this one should have a higher potential, and then okay, it will go through this. But anyway, for this case, you cannot consider it as has a same potential anymore, because we start to consider there should be some resistance in between. Otherwise, as much as this node here and here won't have the same electric potential. So yeah, so the potential difference should start to drop along the path. Okay, so it says if we insert a battery in the loop, the conducting loop is no longer at the same potential. Electric field act inside the material, making up the loop, exerting the force on the external charge, causing them to move, and thus establishing current. So it's like there will be some electric field inside. So in the past, I just mentioned that there's no E field inside. But for this case, if you really put a battery here, then there will be E field inside the conductor. And of course, the moving particle is the electron, and the E field should follow the direction of the current. So in that case, for example, here you can see this is negative charge. So the force acting on the electron should be opposite to the direction of the E field. So F acting on the E should be pointing the other way around. So in this case, it's counterclockwise. Okay, so here is the definition. Is the definition of the current. So yeah, as much as we already know Q is actually the charge at a specific point or specific region. Okay, so if we consider the charge and then take its derivative with respect to time, which means that how much the charge has changed at a specific region. If it becomes larger, then yeah, there will be some current going in it. If the Q becomes smaller, then which means that there is some current going outside a region. Okay, so this is the derivative of the Q of the charge with respect to time will be the current. Okay, so far we already know that for the Q, SI unit should be C, and then for the time, the SI unit is second. Okay, so this one is coulomb per second, but actually we will have another unit as A, which is ampere. Okay, ampere. Okay. Okay, so here we mentioned the Kirchhoff current law. So last time I already mentioned there are Kirchhoff voltage law and also Kirchhoff current law. So when we use the Kirchhoff voltage law for last time, we are trying to use to explain the series capacitance. At that time we used the Kirchhoff voltage law, KVL. Okay, so that is a KVL. This is KCL. So for that time, we try to consider a complete loop, and then we try to consider the potential difference step by step, and then when we add them together in a correct direction, and then it turns out to be a zero for a complete loop. And then for this one, Kirchhoff current law, which means that when we consider the current for the circuit, for example, for this junction, okay, this is called a junction or a node or a junction or a node。A node 就是节点，或者是 junction 就是一些交叉点嘛，就是这样。Okay, 然后and then yeah, when we consider the current going in and going out, so there may be some current going in, there may be some current going out. Okay, so if we consider the total current going in, so in this case there are only 3 branches for this junction. This one is going in, these 2 are going out. Maybe for more complicated circuit, there may be like a 3 current going in, 2 current going out. But yeah, here it says the total current going in a node must be the same as the total current going out a node. Okay, so that there won't be any charge accumulating at the junction. Okay, so let's see. It says because of charge is conservation of charge, the magnitude of the current in the branch must add to yield the magnitude. Yeah, current in, and then yield the current in the original conductor, so that the current in the branch must add to yield the magnitude of current in the original conductor. Okay, so which means that the total current going in equals the sum of the total current going out. Yeah, actually when I do the calculation for the circuit, usually I won't consider some current going in, some current going out, then it's easy to make mistakes, because at the very beginning you usually don't know whether the current is going in or going out. Yeah, this is usually not possible to know that beforehand if the circuit is complicated enough. Of course, for the circuit as simple as this, you of course can know the current direction should be like clockwise. But yeah, for more complicated circuit, you might not be able to know what is the current direction. So usually for me, I will usually define all the current are going out. Define all the current going out, and then the summation of them will be 0. The summation of them will be 0, because if you define all the current going out, then there will be no current going in. So the current going out will be 0. Or the other way around is okay. If you define all the current is going in, then no current is going out. Then total current going in is 0. Okay, but yeah, you may ask, for the practical case, there may be some current going in, some current going out. So if the current is, if you define all currents are going in like this. If you find a positive current, then it is going in. Positive current, then it is going in. If you calculate it to be a negative value, negative current, then it will be going out. If this is out, then it is the other way around. So it doesn't really matter whether you define the current is going in or going out. So if you define some current going in, some current going out, then there may be some positive, negative, and then you will easy to make mistakes. So for me, I just define all the current going in or all the current going out. Then okay, I just only need to play with a plus or minus sign one time. So yeah, it will be easy to less possible to make mistake at least. Okay, so here we will define what is the current density. Okay, current density is 电荷密度. Okay, so yeah, so this definition is very strange. Usually when we try to define a variable, it should be like, if we try to define what is f, it should be f equals to something. Then we try to define f. But here, we try to define the current density J vector. But actually it is put inside a surface integral. Okay, because yeah, it is not easy to define J by writing an equation as J equals something. It is not easy because this is the other way around. So when we try to integrate the current density, it will be the current. So for example, if we consider the surface is like this, or maybe the surface is like this, we can calculate yeah, of course, yeah, these purple line are like the J vector field. So for example, this surface 1, 2, 3, you may be able to calculate the J dot dA integration and then become the current. So you can calculate the current going through here, or through there. But they should be the same because the charge cannot be stay there. Yeah. Of course, this is a surface integral, so you can define dA to be in this direction or the other way around. So yeah, it doesn't really matter. It's just up to your definition. For the Gauss law, because it is a closed surface, it can define which side is outside. So dA should pointing outside of a surface. But here, as much as this is not a closed surface, so you can either decide either direction to be the direction of dA. But of course, you should all the way follow what you define. You cannot calculate this part dA point to the left side or that part dA point to the right side, then you'll be wrong. So you must be all the way off. For example, for this one, you consider dA point to the right side, point to the right side, point to the right side. Yeah. Okay. So so it says the current density has the same direction as the velocity of the moving charge if they are positive charge, and then the opposite direction if the moving charge are negative. Negative. Yeah. So it is trivial, I think. Okay. So here we'll come up with equation, which is like some hardcore physics. When I learn the physics too, yeah, actually not in but yeah, actually when I learned the physics too, yeah, I was taught by a physics professor. So at that time, she just told me that this equation is very important, but actually we are engineering student. We are not the science guy. So actually for me, I have never used that later on. But yeah, so for different people, the point of view can be quite different. Okay, for us, engineering guys, so we try to use the theory to solve problem rather than to go deep into some like hardcore physics. But at least we should know a bit about that. Okay, so here when we try to consider the current in a wire, yeah, so here, of course, it's just try to assume that the moving charge are positive. Okay, of course, this is not true. Now we of course know that the moving charge is the electron, which is a negative charge. But for this case, it doesn't really matter whether it is positive charge or negative charge. So yeah, it will give the same conclusion. So it doesn't really matter here. So let's try to follow that. Okay, we just assume that the moving charge is positive. Okay, so here we also assume that the current is going to the left side from the right to left, which means that the positive charge should also moving from the right to left. And in that case, there should be an E field. There should be an E field all the way like this to push the positive charge to the left side. And also the the current density also point to the left side. The current density. So all the vector points to the left side. Okay, very nice. So okay, so here we try to consider how many charge are within this volume. Okay, of course this is a wire. You consider it is a cylindrical shape with some radius. Okay, so here Q is the charge within this volume, and then this is E. This is the elementary charge, which means that yeah, this is like a positive electron. Yeah, of course, a positron really exists, but yeah, not for that case. But at least we assume that the moving particle are like a positive electron like that. Okay, so assuming this is the unit charge, and then this is the number of charge. So here A is the cross section area. L is the length of this cylinder, which means that A times L is the volume. This is the volume, and then this is the volume, volume, and then this is the charge density. Or more specifically, this is a volume charge density. Which means that how many electron or how many charged particle inside a unit volume. Okay, so this is Q equals number of charge times the unit charge amount. Okay, so so next we get this one, T equals L over Vd. Okay, so this is like primary mathematics. Okay, the displacement equal the velocity times the time. Okay, times the time. So this is L, and then this is the velocity, which means that the t is the time for a particle moving from the beginning point to the end. Okay, so this is t. And then yeah, so here we have I equals qt, I equals q over t, I mean. Of course, just now it is like I equals dq dt, but if q is uniform, so it is just like q, or maybe you can consider it is like q minus 0 and then t minus 0, something like that. So it becomes q over t. Okay, so here we try to plug in this one here, n times a times l times e, and then t equals l over vd, l over vd. So we can do some cancellation, which means that we can cancel capital L. So it turns out to be n times e, putting here, and then a times vd. Vd is here, so putting back here, so it goes to the top. So ne times a times vd. Okay, just now we have I equals integration of j dot dA. And of course, if we consider J and A points to the same direction, and J is uniform inside the wire or for the cross section, and it turns out to be J times A. So I equals J times A, so we will have J equals I over A. And then we can actually moving this A to the left side. Moving this A to the left side. So we will have I over A on the left side equals NE over times VD. Which means that I over A is J. So we have J equals NE times VD. Okay. So here it means that E is a constant, of course a unit charge or the elementary charge. This is N, the charge density, which should be a constant for a specific material. For example, if it's a copper, N should be a value. Or just last time I think we have come up with that value. But for different material, the value may be different, but given the same material, the N should be the same. So yeah, so here we will consider the material doesn't change. So in this case, this is a constant, which means that the current density is proportional to the so-called drift velocity. This is so-called the VD is the drift velocity of the current. Drift velocity 这是什么漂移速度啊？漂移速度。Okay. So maybe we stop here today.